So I've got the electromagnetic spectrum here. So make sure you memorize this, memorize the order of this. We've got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Within visible light, we've got the 7 colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. So red is on this side, on the left side, violet on the right side. It all depends on which way you're writing it from. So if you're writing it this way or the other way, with gamma on the left. So frequency increases when you go from radio to gamma. Wavelength decreases when you go from radio to gamma. And red is on the left side of visible. So it's the visible light with the lowest frequency. And if you lower the frequency even more, you go to infrared. That's why it's called infrared. It's next to red. And then ultraviolet is the other way. It's next to violet. So that's a good way of remembering which way around the color goes. Yes, I will upload this at some point as well. Uses, yes, you do need to know the uses. So we've got the uses here. I'll let you screenshot this at some point. So radio waves, communication, Bluetooth, microwaves, communication, that's more like satellite communication. Also in cooking food, obviously, you've got microwave ovens. Infrared, remote controls, night vision. So thermal cameras basically pick up heat. Infrared is heat in the form of waves. So it picks up heat from objects and turns up in night vision. So things that are live, like living things, are mostly giving off heat, so you can see them using night vision cameras. Visible light is just normal light that we use for photography. Here's another one. This is like broadband communication for the internet. We call it fiber optic communication. Then this is GCSE, not A-level, guys. Ultraviolet is for tanning beds and fluorescent lamps. X-rays are obviously for X-rays, for medical imaging, and gamma rays you can use for treating cancer, which is quite ironic because it causes cancer, but you can also use it to kill cancerous cells, and also to sterilize things like medical equipment. Okay, so let's get into the questions then. Here we go. First question. So this is actually an edXL question. So a car accelerates at a constant rate of 1.3 meters per second squared on a flat straight road. The force acting on the car, so we've got the force acting on the car as this, 1.87 kilonewtons. Calculate the mass. So we've got mass, force, acceleration. What equation are we going to use? Here you go, guys. Here's the equation sheet. Take a screenshot if you want. There. Okay, so yes, exactly. We got an equation with force, acceleration, and we're trying to find out mass. So that is going to be F equals ma, which is there. Resultant force equals mass times acceleration. Okay, so write down the equation. F equals ma, and we want to rearrange this to make mass the subject because that's what we're trying to find. If you want the triangle, here it is. F, at the bottom we got m and a. So we're trying to find out m, so cover that up. It's F divided by a. M is equal to F over a. What else do we need to remember to do here? Because we don't just put the numbers straight in, there's something else we need to do. Change the unit. What we have here is kilonewtons. In the equation, the force has to be in newtons. So how can we convert kilonewtons into newtons? So this is relevant to triple and combined as well. Yeah, times by 1,000. So that's the first thing to do. We got 187 times 1,000. So that's going to give you 1,870 newtons. Now we can put everything into the equation. So 1,870 newtons divided by 1.83 meters per second squared. What is the answer when you put that into the calculator then? Anyone got it? So 1,870 divided by 1.83. Anyone got a calculator on them? Yes, okay. So careful with the rounding. So 1,870 divided by 1.83 gives us 1021.85, but that's not our final answer. We can't leave it like this because it says 3 significant figures. If it says that, that means you get a mark for that. If you don't write it to 3 significant figures, you're going to lose a mark. So that would be, yes, exactly, 1,020 is the final answer. So remember to do that if it asks you to. How long's the live going on for? Till 8:45. Okay, next question. I think it links to this, so we'll keep this up as well. The car accelerates from rest for 16 seconds. Calculate the speed of the car. So what do we have here? We've got, we want to work out something with speed. From rest for 16 seconds, we've got time. Rest, and we got it accelerates as well. Calculate the speed. So we know what the acceleration is as well from the previous question. What can we do for this one then? Any ideas what we can do here? Yeah, this is combined. Did I say 3:45? I mean 8:45. Yeah. You would think it's speed equals distance over time, but it's not. There's no distance involved here. They haven't given us a distance, and we don't need to find distance. So we don't use speed equals distance over time. So it's a bit tricky to work out which equation you need here. You don't need 2 equations. You can do this in 1 equation. It is, let me put it this way around. It is this one, acceleration equals change in velocity over time. Because we got acceleration given to us in the previous part here. We got acceleration there. Speed is the same as velocity. So acceleration is equal to change in velocity over time, right? So we can work out the change in velocity using acceleration times time. So let me do a triangle for this as well. There it is. Sorry, what initial velocity is different to change in velocity. Yeah, change in velocity is final velocity minus initial velocity. So final is the velocity at the end, initial velocity is at the start. This change in velocity is just v minus u. So you could rewrite this as, let's write it up here in our notes. So we can, in your equation sheets, it's written like this, delta v over t. But what that also means is v minus u over t. Yeah, where a we know is acceleration, v is final velocity, and u is initial velocity. And t is time. Okay, so back to the question. If we've got delta v over over t, we want to calculate speed. So we want to calculate the final speed, probably, isn't it? Because it accelerates from rest. If it's from rest, what does that mean? From rest means the speed is 0. Yeah. 0 meters per second. So 0 meters per second at the beginning, at the start. So we know the initial as 0. So what you can do is work out delta v, so the change in velocity, by doing a times t, acceleration times time. So we've got our acceleration up here from the previous part as 1.83 meters per second squared. We can times that by the time, which is 16. What does that give? 1.83 times by 16. Uh, 29.28. Is that what you get? Yeah, okay. Let me just try it as well. So 1.83 times 16. There we go, 29.28. So that is the change in velocity, but we know the velocity at the start is 0 meters per second. So if you do this minus 0, you just get that. So that means this is the answer. So, yeah, 29.28 or 29.3 if you want to do it to 3 significant figures. Okay, on to the next one. Here, we've got another question. Some students have designed and built an electric-powered go-kart. After testing this, the students decide to make changes to the design. So we've got one design here, we've got one design here. The go-kart always has the same mass and use the same motor. So you can see here, there's just a change in shape. But the change in shape from going from X to Y will affect the top speed of the car. Why is that? Yes, it is what you're saying there. It's to do with it being more streamlined. Good, that is actually 1 mark. So we can write that there. It's more streamlined. And that means less air resistance. Less air resistance. So what's happening is the streamlined shape is cutting through the air, so there's less air particles hitting against the car and slowing it down. Streamline is, it just basically means the shape and the surface area of the shape. So you see the car, look at the surface of the car that's hitting the air. So if the car is moving to the left, this whole area is hitting the air in the first one, whereas in the second one, it's a very small area. Because it's streamlined, it's like sort of like piercing through the air here. So streamline means the air resistance is less of an effect on it. So those are 2 of the marks, more streamlined less air resistance. Therefore, what's the third mark for? Yeah, goes faster, can reach a higher speed. Can reach a higher speed. That's because in the question, it just says how will it affect the top speed, or why does it affect it? It doesn't say it's going to increase it. They don't tell you that. You're expected to say that in the question. Okay, so yeah, that's why most things that like travel fast things, they're usually shaped like this. They're shaped to be more streamlined and have less air resistance, so you can basically waste less fuel when you're traveling with them. What's air resistance? Air resistance is a force that any object feels if it's traveling through air, because you don't see it, but when an object travels through air, there are air particles here, right? Every air particle, so that's like, it could be oxygen, it could be nitrogen, it could be any particle, any gas particle, they have mass themselves. So you don't feel it, but you have to actually break through them. You need to push them aside when you're going through the air, isn't it? So when you go through a lot of air particles, there's a lot of force needed. The faster you go, the more air particles you need to go through. So that force always acts in the opposite direction to your movement. So it's always going to be acting this way, the air resistance. Okay, hope that makes sense. Okay, on to the next one. So the final design, go-kart Y is entered into race. The graph shows the velocity time graph here. So we got velocity time graph. Use your graph to calculate the acceleration of the go-kart between points J and point K. So we need to find out the acceleration between J and K. So this section here. How do you work out the acceleration of something like that? Yeah, gradient, exactly. So you can work out gradient, or you can do change in velocity over time, because it's changing velocity from 0 to 5, and it's doing it in a certain amount of time. So you can work out the velocity that's changing here. So if you read that, what is the velocity that's changing, and what's the time that's changing? Yep, it's 5/3, because you can read up here, we got a 5 here, and then down here, we got a 3. So it's going to be 5 divided by 3 to get the gradient. Does that make sense to everyone? So calculation, you just do 5/3, which gives you 1.7. So asking for two significant figures, and we've been given the units as well, so 1.7. So that's everything for that one. Next one, use the graph to calculate the distance of the go-kart between points J and K. How do you find the distance on a velocity time graph? Area under it. Yep, good. So here, what you can do is you can look at that triangle. How many seconds was it looking for? Yeah, points J and K, wasn't it? So that makes a triangle. You can work out the area of this triangle. So a bit of maths here. How do you work out that the area of that triangle? So it's not speed over time. If you have a VT graph, a velocity time graph, area under the graph tells you the distance traveled. So velocity time graph, we can say gradient gives you acceleration. And and then the area under the graph. Gives you the distance traveled. So yeah, back to this question. This is a triangle, so we just need to do area of a triangle, which is half base times height. So we've already got the base and the height from before. It was 5 and 3, wasn't it? So you just need to do half times 5 times 3. Oops. Half times 5 times 3. What does that give? Anyone got the answer there? 7.5, yeah. So let's write that down. 7.5 meters. Good. Right, next one. What causes most of the resistive forces acting on the go-kart? I've already said it, right? We said it already. It's air resistance. Air resistance. Yeah, good. Okay, next one. So we got a question here on springs. So we got a student hanging a spring off a clamp, and then you hang a mass on it. So this is the spring without anything on it. Let me zoom in a bit more. That's how it looks like. And then after a mass has been added onto it, so what happens is the spring stretches downwards and increases the length of the spring of itself, basically. The extension of the spring is the distance between the positions labeled what and what on the meter rule. So the extension, looking at that, which points would you say extension is? So people get confused with this. So so look at the original length of the spring, yeah? So imagine we have a spring here. Let me draw a spring. That's the original length of the spring. Then we add a mass and the spring stretches. So distance from here to here, we'll say, that is the original length. Next bit, you need to be careful because you've got two lengths here. The extension is not the length like before. It's not the full length of the spring like before. This is the stretched length. What's the extension then? How do you define the extension on this? How do you draw the... You minus the 2, yeah. So you look at what the original length was. See, the original length is like from here to around here, right? That's the original length. Extension is the stretch length minus the original length. So that is the length from here to here. That's the extension. Okay, so we'll write that down here. Extension is defined as a stretched length. Stretched length minus original length. So back to the question, looking at that diagram here, think about what the original length is. Original length is A to B, isn't it? That's what we can take as original length. Move this back up here. So original length from here to here. So original length here is from A to B. That's not the extension then. Extension would be, what do you guys think? B to C, yeah, exactly, because that's what it's stretched to. You see the point that it's at, it's on the ring, on the ring of the spring. Here is the ring of the spring, so that's the extension from B to C. So it'll be from positions labeled B and C on the graph, the answer. What form of energy is stored in the stretched spring? Why not D? Not D because D is the location of the mass. We have to compare it to the first graph, the first diagram. And in the first diagram, there was no mass. So if the mass would be like down here somewhere. Here we measured it from the ring, didn't we? So here you need to also measure it from the ring. Let me rub it out so you can see clearer. Do you guys understand? That's why it's not D. Does that make sense? Yeah? Okay. And yep, next one is elastic potential energy. Well done. Anything that's stretched, so anything like a rubber band or something that's stretched always has elastic potential energy stored in it. So that's why when you let go, it moves because all of it gets converted into kinetic energy. Next up, the result from this investigation are plotted on the graph. So we got extension against force. What error has the student made looking at this graph? Paper 2 for most people. Paper 2 for most people. I think it's just, is it just Edexcel? That's paper 1. Extension needs to be in the, not necessarily. There's a bigger mistake because having it the other way around is it's not wrong. It's not wrong. There's errors the student has made in the actual experiment that you can tell from these results. What are these graphs supposed to look like? Whenever you have a graph on springs, do you guys remember how it looks like? Starts at the origin. Yes, thanks. It should start at the origin. Whenever you have a graph on springs, you see the equation for springs is force is equal to spring constant times extension. We've got it here. Force equals spring constant times extension. F equals KE. Let me change that to an E because that's how it's written. So this means that F and E are directly proportional to each other. That just means if you double one, the other one doubles. If you half one, the other one halves, and so on. So if you did a force against extension graph or the other way around, like it was in that question, extension against force graph, you get a straight line through the origin. In these diagrams, you always have a straight line and it goes through the origin and then it starts to curve off like this because there's it stops being proportional after a while. If you stretch something too much, it stops being proportional. So it needs to look like this. It needs to be a straight line. At the start anyway, it has to be a straight line through the origin. So back onto the question, we don't have a straight line through the origin. It's going up here. So what error has that student made? That's not the actual error. The reason is because it doesn't go through the origin. So what's the actual error that they've made? So we'll write down here, because the line should pass through 0 or origin. What mistake have they made in their calculations? If here they've got 50. They plotted it wrong. They did plot it wrong. Nope, they didn't have weight on the spring before. Didn't calculate. Yes, they didn't calculate extension properly. That's what it is. Remember what I said? I said extension is original length minus stretch length minus original length. So if at the start, so what they're saying is at the start, when there's nothing on it, see that as 0, nothing on it, it's got an extension of 50. That can't be right. The spring doesn't stretch here. So how can it be 50? So the mistake that they must have made is they said this was 50 and this is the extension, but that's not what the extension is. Remember what I said? There should be no extension at the start because it hasn't extended. It's just its original state right now. So the mistake that they've made is they've used the original length as the extension. Does that make sense? So they measured the original length. Original length instead of the extension. Yeah. Okay, good. Next up, the student has loaded the spring until it's beyond its limit of proportionality. Mark on the graph the line, the limit of proportionality of the spring. Mark on the graph line the limit of proportionality and label it P. Give you a reason for P. So where would I mark it here? Go back to which part? The question or the graph? You guys saying 6.2? Can't be 6.2. No. What are we looking for here? What are we looking for? Which point? And why are we going to pick that point? You want to see the answer again here. Around 5.4. Yes. Why do you pick 5 or 5.4 there? Why is that the point where it's reached limit of proportionality? Because it starts to curve. Yeah. It's no longer a straight line through the origin. It's no longer proportional. For something to be proportional, remember what I said, it needs to be a straight line through the origin. The moment it stops being a straight line, it's no longer proportional. So we need to find the point where it stops being a straight line here. So it's around here somewhere, I'd say. And then read it. Here, so it's around 5.5. So we would mark this as P, that point as P. In the question it asked to mark it at P, you don't need to do this. So that would be the answer. So yeah, it doesn't follow Hooke's law, you can say that as well. So give a reason. You can say it is no longer straight. So no longer proportional. Right. Next, we got another calculation here. The student uses different spring as a spring balance. When the student hangs the stone, its extension is 72 millimeters. It doesn't go past this limit of proportionality. Calculate the force. And we've been given the spring constant here. What equation are we going to use here? Not half ke squared, no. Sorry, let me show you there. Yeah, F equals kx or ke, yeah, F equals ke or kx. This one here, the one I was talking about earlier, not the energy one. So I think someone mentioned this one. That is a very close to it, half ke squared. That's got spring constant, it's got extension, but it's also got energy. This, you use this to calculate energy, elastic potential energy. So it's not that one. I'm holding it the wrong way, sorry. I don't know why I'm doing that. Yeah, this way. So it's not this one, because there's elastic potential energy. It is this one. So F equals ke. We want to work out the force, so there's no rearranging needed. But if you did want to rearrange, here's the triangle. Ke, like that. What else do we need to do here? What do we need to remember? Yep, millimeters to meter. Don't forget that. Every time you're doing a calculation, always remember in your head the steps, write the equation, do the conversions, then put the numbers in. Conversions. 72 millimeters, how do we turn that into meters? Yeah, divide by 1,000. 72 divided by 1,000. So that gives 0.072. Now we can put it all into the equation. 25 times 0.072. Anyone got the answer there? Yeah, thank you very much. 1.8. Okay. Well done, guys. All right. One of the harder topics in physics here. Magnets. This question, we've got two magnets, we've got a wire in between the magnet, and we got current flowing through the wire, or we got a switch that will cause it. Yeah, not everyone, everyone's worst probably this topic. Explain why a force acts on the wire XY when the switch is closed. Yeah, so when the switch is closed, there's a current, that is a mark. The magnetic fields interact, yes, good. Good. Right, so let's write a few notes on this. What do we call this effect? Anyone know what it's called? Motor effect, yeah. So in the motor effect, when you have a current carrying wire, in a magnetic field, the wire experiences a force. So it'll probably move. That's because, so a current carrying wire, so a wire with current flowing through it, it's not generator effect. No, generator effect is basically the opposite of the motor effect. Magnetic field is an area, any area where a magnet experiences a force. So you have a magnetic field around any magnet, because if you bring a magnet close to it, it's going to either attract or repel. That's a magnetic field. It's not something you can see, but anything magnetic will have a magnetic field around it. So what you have here is you have a current carrying wire. So this is your wire. Around the wire, you have a magnetic field, like in the shape of loads of circles. It's not great drawing, but it's loads of concentric circles like that. This is in between two magnets. In that diagram, we've got two magnets. Let me draw the two magnets separately here. We have a north pole and a south pole. I don't know which way around it is. But when you have a north and south pole, you also have a magnetic field that goes between the two. These are arrows that just show that point in the direction of the field. So this one has arrows on it as well. And what happens is this magnetic field is inside this magnetic field, and both magnetic fields start to interact with each other. When the fields interact, it causes a force to be created. That's why all of this happens. So the wire experiences a force, and the reason why because the two magnetic fields interact. What does the force do? It's going to cause the wire to move. So if you were to ever get any, like a real wire with current through it, and you put it between two magnets, that wire is most likely going to move. It's going to move up, down, left, right, in a certain direction, which you can work out, which I'll talk about in a second. But that's what happens, yeah. So it will move. So this question is basically asking you to talk about that. So explain why a force acts on the wire. Because closing the switch causes current flow. Yeah, the left-hand rule, exactly. This creates a magnetic field. Around the wire, and this interacts with the magnetic field from the two magnets. Sorry, with not the two magnetic fields, with the magnetic field of the two magnets. Okay, so next question is Fleming's left-hand rule. So you get a force, right? And it causes X, Y to move. It causes this Y to move. and you need to figure out what direction it's going to move. This is when you use Fleming's left-hand rule. Can anyone tell me which way this is going to move? Do you have to mention the motor effect? Not necessarily. You can say it's the motor effect, but it's asking you to explain it. There's a question later, it says state the effect that it demonstrates. You'd write motor effect here. So someone said to the right. I don't think it's to the right. No, it's not. Let me explain the Fleming's left-hand rule real quick, because this is complicated. People always get confused with this. So what you need to do, you need to hold out your left hand so that your first finger, second finger, and your thumb are all perpendicular to each other. Okay? Like this. Fleming's left-hand rule. So hold your thumb, first and second finger perpendicular to each other. Okay, so each one of these are going to represent something in that diagram. So first finger always points in this direction of the field. So first finger is always in the direction of the field. Second finger is always in the direction of the current in the wire. So do you remember we had our current carrying wire? That's always in the direction of the current. So you line those two up. So you look at your diagram, you line up your first finger with the direction of the field, you line up your second finger with your current, and then wherever your thumb is pointing is where the force is acting, is the direction the wire is going to move. So your thumb is the direction of the force, or the direction of the movement. Okay? So back to our diagram, let me show you how that works. First finger is the field, remember? Second finger is the direction of the current, and this is going to give you the direction the wire is going to move. So here, which way is the current moving first of all? You need to figure out which way the current's moving. We've got a battery here. So in a battery, the longer side is the positive side. The shorter side is the negative side. So which way is it going to move, clockwise or anti-clockwise? The current is going to move clockwise. So this is from electricity. That's from our electricity knowledge. Current always flows from positive to negative. Okay, so current is going to flow in this direction. This is the most important bit here, this section from X to Y. Okay, how do we know that side is positive? The battery, the longer side is always the positive side, the shorter side is always the negative side, because positive is bigger than negative. Okay, so now we know the direction of the current. We have all our information to use Fleming's left-hand rule. So let me remind you again. First finger field, second finger current, thumb is the direction of the force. So line up your second finger with the direction of the current. The current here is going from left to right. So that's like that. And then your first finger is going to go in the direction of the field. What direction is the field going in? What direction do magnetic fields usually go? They always go from north to south, yeah. north to south. So here's the north, here's the south, and the Y is between it. So our first finger is going to go towards north, from north to south like this. Line up the two, and then you can see, look at the direction the thumb's going in, you can see it's coming up out of the page, isn't it? So the Y is moving upwards. So the answer would be upwards, drawing the arrow like this. If the current was going the other way, imagine the current was going the other way. Imagine like this. You're basically doing this with your hand, because current is going to be moving to the left and your thumb's going to be pointing downwards when you do that. It's hard for me to show you with the camera. But if you do it, it's going to be the opposite way and the force will be going downwards. So the answer is the Y is moving upwards. Does that make sense, guys? I might make a video on this because I know loads of people struggle on this. I'll have a think. But yeah, I think we'll leave it there. Let me give you guys a chance to screenshot this. I will put this all on YouTube at some point soon, and you can rewatch everything, and I'll give you a chance to print off the questions and do that as well.